So today we will discuss chemical equilibrium. So equilibrium is the state at which the concentrations of reactants and products do not change with time. It is the state in which the measurable properties of the system such as pressure, density, color or concentration do not undergo any further noticeable change under a given set of conditions. So consider a chemical reactions. We are considering here chemical reaction A plus B goes to C plus D. The forward reaction is A plus B goes to C plus D, and the reverse reaction we can write as C plus D goes to A plus B. As the reaction proceeds, the concentration of the reactants, so we started with the reactants A and B, so concentrations of the reactants decreases and therefore the rate of forward reaction falls off with time. On the other hand, the rate of the reverse reaction or backward reaction increases due to the increase in the concentration of the products. Thus, at equilibrium, rate of forward reaction equals to rate of backward reaction. So, if we plot here concentration versus time, we can see that as time progresses, concentration of A or B decreases like this. So, this is a schematic diagram, and concentration of C and D increases with time. After a certain time here, okay, you can see at here, there is no change in the concentration of either C or D or A and B. So, you can say that the reaction is reached at equilibrium here at this time. Then we discuss law of mass action. In 1864, two chemists Cato, Maximilian Goldberg and Peter Waj suggested a quantitative relationship between the rates of reactions and the concentration of the reacting substances. The relationship is known as law of mass actions. It states that the rate of a chemical reaction is directly proportional to the product of the molar concentrations of the reactants at a constant temperature at any given time. So, we consider a simple reaction between the reactants A and B. So, here we consider reactants A and reactant B, and when they react we get products. So, according to the law of mass action, rate of reaction is proportional to concentration of A and concentration of B as stated by law of mass action. So, if we remove the proportionality sign, so we get a proportionality constant here K. So, rate R is K times A, concentration of A times concentration of B. Now, if we consider that concentration of A and concentration of B are unity, so you can say that R is equals to K. Here we consider A and B are the molar concentration of the reactants and products, and K is the rate constant. So, this K is called rate constant. Thus, the rate constant of a reaction at a given temperature may be defined as the rate of the reaction when the concentration of each of the reactants is unity. So, when concentration of A and B are unity, so rate of reaction is nothing but the rate constant K. So, for a general reaction, suppose small a moles of A, reactant A, plus small b of reactant B and small c of reactant C, they react and we get a product, okay, we get products here, where A, B and C are the stoichiometric coefficient, A, B and C, as I said, stoichiometric coefficients. The law of mass actions may be written as rate of reaction is K, rate constant K to the A raised to the A times concentration of B raised to the B times concentration of C raised to the C. Thus, the law of mass action may be restated as the rate of a chemical reaction at any particular temperature. So, temperature is very important here, is proportional to the product of the molar concentrations of reactants, with each concentration term raised to the power equal to the number of molecules of the respective reactant taking part in the reaction. Then we discuss what is equilibrium constant. So, considering a simple reversible chemical reactions where equilibrium exists between reactants and products. So, reactants A and B, when they react, they form products C and D. So, this is the equilibrium sign here. So, as per the law of mass action, rate of forward reaction, if we say so, it is R is Kf is the rate constant of the forward reaction times concentration of A times concentration of B. Similarly, rate of backward reaction is or reverse reaction, we can say that rate R is concentration of C times concentration of B times rate constant of the backward reaction. So, as I mentioned, so Kf and Kb are the rate constants for the forward and backward reactions. So, at equilibrium, rate of the forward reaction equals to rate of the backward reaction that we already discussed. So, we can write at equilibrium rate of forward reaction equals to rate of backward reaction. So, rate of forward reaction we just derived it, Kf times concentration of A times concentration of B, and the rate of backward reaction is Kb times molar concentration of C times concentration of D. So, they are equal at equilibrium. So, we can write Kf by Kb. If we rearrange this one, if we take Kb this side and AB this side, we get like this. So, Kf by Kb gives concentration of C times concentration of D by concentration of A times concentration of B. So, here Ka by Kb, this term is called equilibrium constant K. So, equilibrium constant K is concentration of C times concentration of D by concentration of A times concentration of B. Remember, this K, this is equilibrium constant, we get when the reaction is at equilibrium. So, in order to calculate equilibrium constant when the reaction reaches equilibrium, so equilibrium constant is nothing but the ratio or if we divide the rate constant of the forward reaction by rate constant of the backward reaction, we get the equilibrium constant. The combined constant K is called the equilibrium constant and has a constant value for a reaction at a given temperature. So, this equilibrium constant is a constant value at a particular temperature. Okay, so it depends on temperature only. So, for a general reaction, so now we consider a general reaction, small a moles of A or small a times A, small a plus small b gives small c times small d, and this is the equilibrium sign. So, when the reaction is at equilibrium, so you can write the equilibrium constant K is as concentration of C raised to the C times concentration of D raised to the D by concentration of A raised to the A and times concentration of B raised to the B, where the exponents A, B, C, D have the same values of those as those in the balanced chemical reaction. So, we need to balance the chemical reaction like this, and then only we can use this equation. Thus, the equilibrium constant may be defined as the ratio between the product of molar concentration of the products. So, you can see the molar concentration of the products, that of the molar concentration of the reactants. So, these are the molar concentration of the reactants with each concentration term raised to a power equal to its stoichiometric coefficients in the balanced chemical equation at a constant temperature. So, this is the balanced chemical equation. So, equilibrium constant K is concentration of the product C raised to the C, this stoichiometric coefficient C here. Similarly, times concentration of D product D to raised to the D by concentration of A raised to the A times concentration of B raised to the B. So, if we consider now the gaseous system instead of aqueous system, we can write in gaseous reaction the concentrations of gases may also be expressed in terms of their partial pressures. So, for the above reaction here, so if we consider these reactions, all the reactants and products are in gaseous states. So, you can write the equilibrium constant can be represented as K times K equals to Pc raised to the C times Pd raised to the D by Pa raised to the A times Pb raised to the B, where Pa, Pb, Pc and Pd are the partial pressures of the gases A, B, C and D respectively. Again, these partial pressures when the system is at equilibrium. Okay. Then next we discuss the reaction isotherm. So, from thermodynamics we know that the change in the Gibbs free energy is related to the composition of reaction mixture. Delta G is delta G naught plus RT ln Q, where delta G naught is the standard Gibbs energy or Gibbs energy and Gibbs free energy, they are synonymous. So, standard Gibbs energy change and Q is the reaction quotient. So, for a spontaneous reaction has negative delta G value that we know at constant temperature and pressure, okay, when T and P are constants. So, the value proceeds to be negative until the concentrations of the products are large and concentration of the reactants small, making the value Q so large that the value of RT ln Q is large enough to offset the negative value. So, as at equilibrium we know delta G is equals to 0, and Q, this term Q reaction quotient becomes equals to the equilibrium constant. So, when the system is at equilibrium, so delta G is 0. So, we already discussed this in thermodynamics. In thermodynamics we discussed at equilibrium delta G is 0 when P and T constant obviously, okay, and delta G equals to delta G is negative for spontaneous change, okay, for spontaneous process. Okay. So, you can see what is Q. Q is nothing but Q is this expression provided the reaction is not reached at equilibrium. So, this is the value, this is the Q here, okay, when system is not at equilibrium, this is the Q. Okay, so this is the Q. So, as reaction proceeds, so this one, or if you consider this one as reaction proceeds in the forward direction, so concentration of C and D increases and concentration of A and B decreases, right. That is why the, okay, so for spontaneous change delta G is negative. So, the value proceeds to be negative until the concentration of products and large reactants are small, making the value of Q so large that the value of RT ln Q is large enough to offset the negative value. Okay. So we got value. So, when at equilibrium delta G is 0 as I mentioned, so Q becomes QC, reaction quotient becomes equilibrium constant. So, from equation 9 here, so from equation 9 here we can write, we can put now delta G is 0 here. So, we get 0 equals to delta G naught plus RT ln Kc. Kc we are considering equilibrium constant here. So, if we rearrange this, we get delta G naught is minus RT ln Kc. Okay. So, if we know the value of delta G, we can actually calculate the equilibrium constant. Delta G naught we can calculate actually value of delta G naught, or other way, if we know the value of delta G naught, we can calculate the equilibrium constant Kc. And if this is log E base, ln is log E base. So, if we consider a log 10 base, we get delta G naught is minus 2.303 RT log Kc. So, this is the Van 't Hoff's reaction isotherm. So, the above reaction, so this reaction we can write, we can rearrange. So, ln Kc is minus delta G naught by RT, right. Next, we discuss the last Chatelier principle. It states that the change in any factors that determine the equilibrium conditions of a system will shift the equilibrium in such a manner so as to reduce or to counteract the effect of the change. This principle is very helpful in predicting qualitatively the effect of change in concentration, pressure or temperature on a system in equilibrium. This is applicable to all physical and chemical equilibrium. Let us now apply last Chatelier principle to explain the effect of changes in concentration, temperature and pressure on various reactions in equilibrium. First, we consider external effects of equilibrium, means effect of change of concentration. So, to explain this, let us consider this reaction. So, H2 plus I2 gives 2Hi. So, suppose at equilibrium a little amount of H2 is added. So, after reaching the equilibrium for this reaction, if we add H2, so the concentration of H2 is increased. Okay. So, if you go back and check, so this is the expression of K here. Okay. So, if we increase the concentration of one of the reactants, here reactant is in this reaction, reactant is hydrogen. So, equilibrium, in order to make the equilibrium constant K fixed, so we need to produce more products, right. Okay. So, according to last Chatelier principle, the equilibrium will shift in the direction in which the concentration of H2 is decreased. So, if we add more H2, we will be getting more Hi. As a result, a new equilibrium will be set, and the equilibrium will shift in the direction which can consume H2. This is possible if more H2 is used up in combination with I2 to form more HI. Thus, equilibrium will shift in the forward direction. So, if we add one of the reactant, either H2 or I2 in this reaction, so reaction will move in the forward direction to maintain equilibrium at a particular temperature in order to maintain the value of K constant. Then we discuss effect of change of concentration. Okay, so the reaction quotient we know Q is HI is raised to the 2 by concentration of H2 by times concentration of I2. So, at equilibrium Q equals to QC. So, if H2 increase, Q becomes less than Kc. So, if we increase H2 here, H2 is in the denominator. So, Q, okay, value of Q will be less than Kc. So, the reaction moves in the forward direction, H2 and I2 decrease and HI will increase, right. So, move in the forward direction here. Okay. So, we get until Q becomes again equals to Kc, again reaches. Similarly, if HI increases, so if we add HI in the here, so we have now more product, so reaction will move or will take place in the backward direction, right. Similarly, if HI increases at equilibrium, the reaction will go forward, will go backward. So, increase in concentration of any of the reactants shift the equilibrium in the forward direction. So far whatever we discuss, and if we increase the concentration of the product, shifts the equilibrium in the backward direction. Next we move to effect of change of temperature. So, to explain this, let us consider this reaction. Nitrogen plus hydrogen gives an ammonia, and the forward reaction is exothermic. So, the backward reaction is endothermic in nature, right. And delta H naught value is for this reaction is also given. Delta H naught is standard enthalpy change. Okay. Suppose the temperature is increased, so the equilibrium will shift in the direction where heat is added, that is towards endothermic reaction, which tends to undo the effect of heat added. If we give heat to the system, so the reaction will move in the backward direction, right. Since the backward is endothermic, so the backward will be favored on increase of temperature and less amount of NH3 will be there. Okay. So, if we add heat from outside, since the backward reaction is endothermic in nature, so the backward direction will be favored. Okay. So, increase in temperature. So, what we discuss now, increase in temperature. If we increase the temperature, the equilibrium will be shifted in the direction of endothermic reaction, right. And if we decrease the temperature, the equilibrium will be shifted towards exothermic direction. Next, we discuss effect of change of pressure. So, again we consider the previous equation like N2 plus 3H2 gives 2NH3. So, according to La Chatelier principle, the increase of pressure will at equilibrium will shift the equilibrium in the direction in which the pressure is reduced. So, on increasing pressure, the volume occupied will decrease, and as a result there will be large number of moles of gaseous substance per unit volume. The effect of pressure can be undone if the equilibrium shifts in the direction which produces less number of gaseous molecules. So, if we increase the pressure, so in the reactant side we have suppose 4 moles of total 4 moles of gaseous molecules, 1 mole NH2 and 3 moles hydrogen gives 2, and in the product side we have 2 moles of ammonia. So, if we increase the pressure, so in order to nullify the effect of pressure, the reaction will move in the forward direction, because here we have only 2 moles. Okay. So, 2 moles and then here we have 4 moles. So, the effect of pressure can be undone if the equilibrium shifts in the direction which produces less number of gaseous moles. Here, since the number of moles of product is less, here equilibrium will shift to forward direction, right. And for this reaction, suppose N2O4 goes to 2NO2, if we increase pressure here, the backward reaction will be favored, right. So, because in the reactant side we have 1 mole, in the product side we have 2 moles. So, here the equilibrium will shift to backward direction as the number of moles of reactant is less. So, for this reaction, if we increase the pressure, we get more of reactant N2O4, and for this reaction if we increase pressure, we get more product. Okay. So, product formation will be favored, more product means more NH3 here. So, in gist, okay, so if we increase the pressure, shifts the equilibrium in the direction of lesser number of gaseous molecules, and if we decrease the pressure, equilibrium will be shifted towards the larger number of gaseous moles. Then we discuss the effect of change of volume. Okay, so if we increase the volume, the equilibrium will be shifted in the direction of larger number of gaseous moles. Okay, that is quite this effect of this effect of volume is just opposite of effect of pressure, and decrease in volume shifts the equilibrium in the direction of lesser number of gaseous molecules. So for this reaction, N2O4 goes to 2NO2. If we increase the volume, okay, if we increase the volume, so the reaction will be favored in the forward direction, and if we decrease the volume, the backward reaction or formation of N2O4 will be more favored from NO2. So increase in pressure means decrease in volume. So the effect of volume will be opposite to that of the pressure. That's what we just discussed. Next, we discussed effect of catalyst. So catalyst has no effect on equilibrium. This is because catalyst favors the rate of forward and backward reactions equally. Therefore, the ratio of the forward to reverse rates remains same, and no net change occurs in the relative amount of reactants and products at equilibrium. What it says is, as we just discussed, equilibrium constant, if we say K equilibrium is K forward by K backward, okay, so equilibrium, so rate constant of the forward direction by rate constant of backward direction. So if we increase the if we add catalyst here, so rate of forward direction as well as the increase of rate of forward direction and rate of increase of rate of backward direction will be the same. So effectively there will not be any change in the equilibrium constant. So catalyst has no effect on the equilibrium constant value. So now we discuss some problems here. The first problem is for the reaction N2 plus O2 goes to 2NO, calculate the equilibrium constant. At equilibrium of 800 Kelvin temperature, the concentrations of the species are N2 is 4 times 10 to the minus 3 molar and O2 is 3.2 times 10 to the minus 3 molar and NO is 2.9 times 10 to the minus 3 molar. Okay, so how do we proceed? Okay, the reaction is, so the reaction is N2 plus O2 gives 2NO, right? This is times, these are all times, okay. So the equilibrium constant for this reaction can write K is concentration of product. So NO is the product raised to the 2 divided by concentration of N2 times concentration of O2. And we know the values of N2, O2 and NO, so we will substitute those values here. So we write concentration of NO is at 2.9 times 10 to the minus 3 raised to the 2 by 4 times 10 to the minus 3 times 3.2 times 10 to the minus 3. Okay, so if we do it, we get 0.657. This is the value of equilibrium constant. This was very easy problem. Next, the equilibrium constant for the of a reaction looks like this. Give its chemical reaction properly balanced. This is very easy problem. So from this equilibrium constant, so this is the value of equilibrium constant, or this is the expression of equilibrium constant. So NH3 raised to the 4, O2 raised to the 5 by concentration of NO raised to the 4, concentration of H2O raised to the 6. So these are for products. So numerator is for products and denominator is for reactants, right? So reactants are NO plus H2O and products are NH3 and O2, right? And this power of reactants and products are the stoichiometric coefficient. So, for NO the power is 4, for H2O power is 6, for NH3 power is 4, for O2 power is 5. So, this is the balanced chemical reaction. A reaction AB2 goes to A plus 2B is carried out in a 20 liter flask at 298 K. Initial moles of AB2 is 0.4 mole. After equilibrium, the total pressure is 1.3 atmosphere. Calculate Kp. So, what is the value of Kp? So, Kp we know. Kp is partial pressure of products. Okay, so partial pressure of products. So, Pa, partial pressure of product Pa times partial products of Pa times partial products of Pb square by partial pressure of AB2. That was the value of Kp. So, we need to convert this partial pressure in terms of mole fraction. So, what is partial pressure of A? Now, partial pressure of A we call Pa right here. So, Pa is mole fraction of A times total pressure. So, P is the total pressure at equilibrium, and Xa is the mole fraction of A at equilibrium, mole fraction of A at equilibrium. Similarly, partial pressure of B we can write is Xb times P. So, again Xb is the mole fraction of B at equilibrium and P is the total pressure at equilibrium, and partial pressure of AB2 is XAB2 times P. So, we substitute all this here, we write Xa times P times Xb times P by raised to the 2 by XAB2 times P. So, we get Xa times Xb times P raised to the 2 by XAB2. So, this is the value of equilibrium constant Kp. Now, we need to use those data. Okay. What is your reaction? Okay. So, reaction is AB2 gas gives A gas plus 2B gas. Okay. And if we consider Y is the number of moles of A formed at equilibrium. So, initially we have 0.4 moles. Initial moles of AB2 is 0.4 moles. So, initial this is 0, and if we consider that all Y moles are formed. So, this is 0.4 minus Y, this is Y, and this is 2Y, right. So, total you get this is number of moles. So, total in total is 0.4 minus Y plus 2Y. So, it gives 0.4 plus Y. So, this is the total number of moles. Now, if we assuming that the mixture behaves ideally, we can write N total is PV by RT. right? Okay, so P, value of P is given 1.3 atmosphere, okay, and V is also given 20 liters times 20 liters. R, so R value we need to take from liter atmosphere unit of R we need to take, so 0.082 liter atmosphere mole to the minus 1 K to the minus 1 times temperature. Temperature is given 298, right? So 298 K. So if we calculate this, we get N total is 1.063. This is the value of N total. So total number of moles. So if we substitute this total number of moles, okay, so we get value of Y. Okay, so we get the value of Y. So 1.063 is 0.4 plus Y. From here we get this one, right? Okay, so we get from Y we get 0.663. That is the value of Y. Okay. Now we need to calculate XA, XB and XAB2. Okay, so XA is 0.663 by total number of moles is 1.063. Oops, is 1.063. We can calculate by using this one, or you can directly substitute the values of, you can convert this one as, so XA is nothing but, we can write NA times NB times P square by NAB2 times N total square. Okay, so we can do it like this way also. So if we do it, we get basically, now we substitute the value. So we get Y times 2Y square times 1.3 square by 0.40 minus Y times 0.40 plus Y plus 2Y. Oh, this is not Y, this is 2Y. Okay, I did a mistake here. So this is 2Y, so this is divided by 2 here. So by 2Y square. Okay, so we get the value of Y, we substitute everything here. So if we do it, we get what is the value of Y, just we can calculate. So Y is 0.663 by 2, so it gives you 0.3315. This is the value of Y. Okay, now you substitute everything here, so we get the value 31.02 times 10 to the minus 2. So this is the value of equilibrium constant we get. Problem number 4 says a chemical reaction given by I2 goes to 2I, a pressure of 105 Pascal and 298 K temperature, the iodine vapors contains 30% by volume of iodine atoms and the rest I2. Calculate Kp. So partial pressure of I atoms, if we say this is Pi is 10 to the 5 times 30%, right? So I 100. Okay, so we get 0.3 times 10 to the 5 Pascal. Okay, and partial pressure of because in order to calculate Kp, so the expression for Kp contains partial pressure of I and partial pressure of I2. So we need to calculate partial pressure of I2 also. So, partial pressure of I2 is 10 to the 5 times 70 by 100. So, we get 0.7 times 10 to the 5 Pascal. So, Kp, so the equilibrium constant Kp Kp is partial pressure of I raised to the 2 by partial pressure of I2. So, if we substitute this, we get 0.3 times 10 to the 5 raised to the 2 by 0.7 times 10 to the 5. So, we get 0.128 times 10 to the 5, or we can write it 1.28 times 10 to the 4. So, this is the value of equilibrium constant. Problem number 5 says, for the formation of NH3 from N2 and H2 at 700. Okay, so problem number 5 says, for the formation of NH3 from N2 and H2 at 700 K is 5 times 10 to the minus 2. If the concentration of H2 is 0.25 moles per liter and NH3 is 0.05 moles per liter, find the concentration of N2. This is again very simple problem. So, the reaction is N2 plus H2 gives 2NH3. So, basically 3H2, N2 plus 3H2 gives 2NH3. So, equilibrium constant K is concentration of NH3 raised to the 2 by concentration of N2 times concentration of H2 raised to the 3, and the value is given. So, for the formation of this at equilibrium constant is K is equilibrium constant K is this. Now, what is the concentration of NH3 is given, right? So, is 0.05 moles per liter. So, moles per liter raised to the 2 by concentration of N2 we need to calculate, and concentration of H2 is also given 0.025 moles per liter to the 3, and value of equilibrium constant is given 5 times 10 to the minus 2 is 0.05 times 0.05 by concentration of N2 times 0.025 times 0.025 times 0.025. So, concentration of N2 is 0.05 times 0.05 by 5 into 10 to the minus 2 is 0.025 times 0.025. So, if we calculate this, we get concentration of N2 is 3.57 moles per liter. We move to problem number 6. It says a chemical reaction of CO and CO2 in equilibrium. Here CO and CO2 in equilibrium with solid carbon has 90% of CO by mass. This exists at 1127 Kelvin and 1 atmospheric pressure. Calculate Kp. So, we start with let the total mass of the mixture of CO and CO2 is 100 gram. Then CO is 90 gram, right? 90%. So, CO is 90 grams and CO2 is 10 gram, right. So, moles of CO So 90 by molar mass of CO, this is 28, so it gives you 3.214. Now moles, or number of moles of CO2 is 10 grams. So 10 divided by molar mass, so molar mass is 44, so it gives you 0.227. So the mole fraction, because we need to calculate Kp, in order to calculate Kp we need to calculate partial pressure, and in order to calculate partial pressure we need to calculate mole fraction, right. So mole fraction of CO is, so carbon here solid, okay, here carbon is the solid in solid state, so it does not contribute in partial pressure, okay. So mole fraction of CO is 3.234 or 3.214 by 3.214 plus 0.227. So if we calculate this one, we get 0.9107. So the mole fraction of CO2 is 0.227 by 3.214 plus 0.227. So we get 0.089. Okay, so we got the partial pressures, we got the mole fraction, so we can calculate partial pressures. Okay, so partial pressure of CO is, if we consider partial pressure of CO is PCO, is total pressure is 1 atmosphere times mole fraction of CO is 0.9107, so we get 0.9107, or you can write 0.911, okay, you can approximate this one. Similarly, partial pressure of this atmosphere, similarly partial pressure of CO2 we can write PCO2 is 1 atmosphere times 0.089. So we get 0.089 atmosphere. So Kp is very easy. So Kp is partial pressure of CO raised to the 2 by partial pressure of CO2. So partial pressure of CO is 0.911 raised to the 2 by 0.089. So if we calculate this one, we get the value of 9.324. Problem number 7 says, for the reaction C plus H2O, C in solid state, gives CO plus H2O. The change in Gibbs free energy is minus 7.1 kilojoule per mole at 1000 degree Kelvin. Find the equilibrium constant. So at equilibrium, delta G is 0, so it gives you delta G naught is minus RT ln K. K is the equilibrium constant. Okay, so we can calculate K very easily from there. T is given, so T is 1000 Kelvin. Delta G naught is minus 7.1 kilojoule per mole. So we can convert into joules. So 7.1 times 10 to the 3 joules per mole, and value of R is 8.314 joules per mole per Kelvin. So delta G naught value is given in joule per mole, so we need to consider value of R in joule unit. So, if we substitute everything here, we get minus 7.1 times 10 to the 3 is minus 8.314 times T is given 1000 ln K. So, you get ln K is minus becomes plus 8.314 by is 7.1 by 8.314. So, value of K we get e to the 7.1 by 8.314. Okay. So, from there we can calculate the value of K, and the value of K here is 2.35. Okay. So, K is 2.35. So, this was a very easy problem. We need to just use the Gibbs free energy in order to calculate the equilibrium constant. Next, we move to problem number 8. It says, for the reaction 3/2 O2 gives O3, find the change in Gibbs free energy at 298 K. The equilibrium constant is 2.49 times 10 to the minus 29. So, here this problem is just opposite to the problem we just discussed, problem number 7 rather. So, we know at equilibrium delta G naught is minus RT ln K. Okay. Here T is 289 K and R is 8.314 joules per mole per Kelvin, and we need to and value of K is given, equilibrium constant K is 2.49 times 10 to the minus 29. If you substitute all this quantity in this expression delta G naught, so you get delta G naught. So, R is 8.314, you have the minus sign here, times temperature is 289 and then ln 2.49 times 10 to the minus 29. This is the everything will be in. So, value of R is joules per mole per Kelvin and temperature is Kelvin. Okay, so, we get the unit is joules per mole. Okay, so, if we calculate this one, we get 163.2 kilojoule per mole. So, that is the value of delta G naught. Next, we move to problem number 9. It says, for the reaction NO plus half O2 gives NO2, find the standard change in Gibbs free energy at 298 K and then the equilibrium constant. Given the standard free energy of NO2, NO and O2 are 58 kilojoule per mole, 88 kilojoule per mole and 0 kilojoule per mole respectively. So, the data given are given delta G naught NO2 is 58.0 kilojoule mole inverse. So, we get 58. Okay, we leave it like this. Then we also got delta G naught NO is 88 kilojoule per mole and delta G naught O2 is 0. So, delta G naught, okay, so the reaction is NO gas plus half O2 gas is in equilibrium with NO2 gas, right. Okay, so, delta G naught for this reaction, So delta G naught is delta G naught of products minus delta G naught of reactants. Okay, so delta G naught NO2 minus delta G naught NO plus half times delta G naught O2. Now we substitute the values of delta G naught NO2, delta G naught NO and delta G naught O2. So delta G naught NO2 value is 58.0 and delta G naught is 88 kilojoule per mole. So you get minus 30 times 10 to the 3 joules per mole. So this is the value of delta G naught. So once we got that value of delta G naught, we can easily calculate the value of equilibrium constant because temperature is given. Okay. So we know delta G naught is minus RT ln K, where K is the equilibrium constant, where K is the equilibrium constant. Now we substitute the value of delta G naught. This is minus 30 times 10 to the 3. This is in joule per mole unit value of delta G naught is. So for the R also we need to use the joule unit. Okay, so minus 8.314 joules per mole per Kelvin, and we multiply with temperature Kelvin, so we get joules per mole. So 298 ln K. So ln K is 30 times 10 to the 3 by 8.314 times 298. Okay, so if we do it, we get the value of K. So K is e to the 30 times 10 to the 3 by 8.314 times 298. If we further simplify this one, we get the value of equilibrium constant is 1.807 times 10 to the 5. Okay, this is problem number 9. Problem number 10 says, for the reaction 2SO2 plus O2 gives 2SO3 plus heat some 180 kilojoule. Which direction will the equilibrium shift as per Chatelier principle? Increase in temperature. So here, okay, shift is here heat is produced, right? So if we increase the temperature, so the reaction will be in the backward direction, right? So the first case, with increasing temperature, or when temperature increases, the reverse reaction is favorable. Because the excess heat has to be absorbed, right? Reverse reaction is favorable, or the reaction will shift in the reverse direction. The reaction will shift in the reverse direction. Or the reaction, okay, the equilibrium will shift in the equilibrium. The equilibrium will shift in the reverse direction. Next, decrease in pressure. So this is gaseous reaction. So if we decrease the pressure, so the reaction will move towards that direction where we get more number of moles, right? So the reaction will move in the again reverse direction. So when pressure decreases, again the equilibrium will shift in the reverse direction. equilibrium will shift in the reverse direction. And third is when we add catalyst. So, adding catalyst, no effect, right? We just discussed no effect. We move to next problem, problem number 11. It says